In this video, we're going to discover something called the sine rule. At the beginning, I would like you to pause the video and look at this triangle and try to investigate if there is a relationship between the sides of this triangle and the sides of the opposite angles. So investigate 5.39 and sine 51.34, 6.4 and sine 68.2, 6 centimeters and the sine of 60.46. You can pause now. Again, if you've reached a conjecture, why don't you try with this triangle again and see if your conjecture works. You can pause again now. So what you've done now is that you have explored and you made a conjecture on the first triangle. Then I hope that you verified that your conjecture works using another example. Now it's time to prove the conjecture. And I hope that you have established something of the sort: A divided by sine of the angle A is equal to B divided by sine of the angle B is equal to C divided by sine of the angle C, or any variant of this relationship. To prove this relationship, which is our conjecture, we take a general triangle ABC with the vertices as shown and with the side lengths as shown as well. If we drop the altitude h from C to the base AB, we will end up with two right angle triangles. This one and this one. Taking the yellow triangle, and because it's a right angle triangle, we can say that sine A is equal to h over b, which is the opposite over the hypotenuse. Well, taking the purple triangle, we have sine b is equal to h over little a. Now we notice that h exists in both equations, so we change the subject and we make h the subject of the first equation, giving us that h equals b sine a. And here we have h equals a sine b. Now those two equations tell us that b sine a is equal to a sine b. With a little rearrangement, we can end up with a divided by sine a is equal to little b divided by sine b, or sine a divided by a is equal to sine b divided by little b. But what about sine b and c? Well, to do that, we look at the same triangle, but we drop another altitude in that triangle, L in this case, and we notice that it splits the triangle into two triangles, this one and this one. And in a similar way, we can find that L is the common between them, and we can find the relationship between sine A and sine C. We end up with this. You can try it on your own, but from this altitude we get sine c divided by little c is equal to sine A divided by little a. And if you combine this result with the previous result, you can add at the end here sine c divided by little c, as in this form. Now this is a very useful result because it allows us to solve triangles that are not right-angled triangles. If you look at this triangle, it's an 8-12 centimeters and 78 degrees angle, but we have no idea if there are right angle in it, and we don't care. So what we can do is we can label the sides A, B, C, and this would be little b, this would be little a, and let's say we want to find the angle B, which is the only one that we can find. So sine capital B divided by little b, which is 8, is equal to sine 78 divided by little a, which is 12. Therefore, sine B is equal to 8 sine 78 divided by 12. And in order to discover what this is, we go to 8 sine 78 and we divide that by 12 and we find the inverse sine, so shift sine of the answer, and this tells us that B is equal to 40.7 degrees, more or less. So if this is 40.7 degrees, we can work out the third angle. And if we work out the third angle, we can apply C over sine C equals one of those, and we can work out the length of the side AB as well. Let's take another example. In this case, we have two angles, and that means that we have the third. This is 87, the sum of those two angles is 87, so this would be 93 degrees. And we can proceed to find the lengths of the sides. In this case, let's say 11.5, we don't even need to label because we're getting quite good at this. 11.5 divided by the sine of the angle that it subtends is equal to a certain length, which is this one. So this should be divided by sine 93. Therefore, L equals 11.5 sine 93 divided by sine 52. And 11.5 sine 93 divided by sine 52 is equal to 14.6 centimeters approximately. And it makes sense. This is a longer side and it subtends the larger angle. We can do the same process to find the length of the side that's oppositely 35 degrees. Consider this case. Let's say that we started out by trying to find the angle B. In this case we have the three sides that are known and we have one known angle. So we have no choice but to start with 5 divided by sine 23.96. Now, if we say that this equals 9.85 divided by sine B, and we make sine B the subject, this will give us sine B equals 9.85 sine 23.96 divided by 5. And if we work this out, we find that this is 9.85 sine 23.96 divided by 5. This equals something, and let's find the inverse sine in order to find B. And we find that B is 53 degrees. Now, looking at this triangle, it's obviously not the case, because the angle B looks obtuse, and actually it's the biggest angle and it's opposite the biggest side. So what have we done wrong? But if you think about it, we know that sine B is this number, gives us two possibilities for the angle B. B is, let's say, approximately equal to 53, but we also know that the angles of the sines of supplementary angles are equal. So B can be 53 or 180 minus 53 degrees, which is 127 degrees. And this seems a logical answer because 53 and 127 have the same sign. So the thing is, how do we know if our triangle is not drawn to scale? If it's just a representation, how do we know? The trick here is to not start by finding the angle B, which is opposite the largest side. Because if there is an obtuse angle in this triangle, it's bound to be this one. In any triangle, there can only be one obtuse angle. You cannot have two. So if this angle is the one that's going to be obtuse because it's the one opposite the biggest side, then don't find its sign first, because you will have two possible answers. You are advised to find the sign of this angle first, and then by subtraction from 180 you find this angle. And let's do this quickly here. So 5 divided by sine 23.96 equals 6 divided by sine C, and by manipulation you get sine C equals 6 sine 23.96 divided by 5, and if we do that on the calculator, 6 sine 23.96 divided by 5 equals this amount. So we find the inverse sine of the answer, and this gives us 29. So C equals 29 degrees. Now if this is 29 degrees and we round this to 24, then our angle here is equal to 180 minus 24 minus 29, and this is your 127 degrees. So by subtraction we know that it's obtuse. So to sum up, the sine rule can be applied to any triangle, but for right angle triangles it's a waste of time. In this case, simply use that the sine of the angle is the opposite over the hypotenuse. In order to apply the sine rule, you need one known side and one known opposite angle, and at least one other piece of information. And finally, if you have a choice of which angle to begin with, as in the previous example, you should start by finding the angle that cannot be obtuse and then work out the last angle by subtraction from 180.